So the next problem for integer programming that we're going to look at is called the fixed charge problem. So charge means money charge. So many decisions result in a fixed or a lump sum cost being incurred. The cost to lease, rent, or purchase a piece of equipment or a vehicle that will be required if a particular action is taken. So we are going to look at the problem where we have to pay setup costs in order to produce, or and then the problem can be applied for the case where the cost to construct a new production line that will be required if a particular decision is made, and also the cost of hiring additional staff that will be required if a particular decision is made. So let's look at the first problem. So we have the problem. We have three products to consider, and we want to maximize total profit. Okay, and these three products are related together by because they are using some common resources. So we are limited by the amount of resources that we have, and X1, X2, X3 can be considered as a number of units produced. Um, and so we can say that the first function, there's a fixed cost. So we have to pay a fixed cost of 500 to produce X1. X we can look at them as location 1, location 2, and location 3. So if we decide to produce at location 1, we earn the unit profit of 52, but we have to pay a fixed cost of 500. And the same for location 2 and location 3. Okay, so the problem with condition 2, 3, and 4 is that they are nonlinear. Okay, so they are nonlinear constraint. So we want to change the nonlinearity to linear ones. So in order to model fixed cost using integer variables and linear constraint, we create three new variables. So we create binary variables W1, W2, and W3. So Wi is 1 if we produce at location I, and then it's zero if we don't produce at that location. So because x1, x2, and x3 is less than or equal to 330, so we know that all these x's have the upper bound of 30. Okay, so we can write 2 to 4 as like x1 less than or equal to 30 times w1, and so on. And the reason why this work is that if we don't produce at that location, so if w1 is 0, then it automatically force x1 to be 0. Okay, so I'm going to write, so if wi is 0, then xi must be 0. But if wi is 1, then xi can be anything that is less than or equal to 30. Okay, so so now we are going to put this condition instead of the 2, 3, and 4. So we have we maximize minus 500 W1 for location 1, location 2, and location 3. And the common resources are the same. And then we also have X1 less than or equal to 30 W1, and so on. And the W are binary, and the X's are non-negative integers. So we can solve for this problem on Excel. So the decision variables are up here, and then we put the unit profit of 52, 30, and what is the other one? 20. And then the fixed cost is 500, and then 400 for 2, and then 300 for 3. And then we just put a constraint of 2, 4, 5, 1, 1, 1, and then 10, 5, 2. And then the mi is just a large number that is an upper bound for all the x's. So we have these as decision variable. So these are decision variable. And then we also have these as a decision variable. Okay, and so we just do m times wi times b17, and then we just drag that out. And then we want the decision variables to appear on one side. So we just do x minus m times w. Okay. So we want to maximize total net profit. So we sum product of the fixed cost. So we have to do a negative. We have because we pay for the setup cost, and then we multiply with the unit profit, and then we have to figure out the amount of resource used. So this, and then this. We have to fix the row 5. Oh, sorry. And then I just drag them down. And then available is 130 and 204. Okay, so I think I'm all done. I'm going to specify the solver. So I want to here maximize total profit, and then changing variable cells are these. Now we have two set of changing variables and this. Okay, and then constraint is that resource use cannot exceed resources available. And then the x minus mwi less than or equal to 0. And then we also have to say that these x's are integer, and then the wi is binary. And then the greater than or equal to 0 is already here, make unconstrained variables non-negative. So we don't have to specify that x's are greater than or equal to 0. And then we click solve. So we can see that we only produce at location 1, and we produce 20 of them, because if we produce one more unit, then we run out of this resource. So the answer is that we only choose this one. Wait, hold on. Where is that? So we only locate at location 1, producing 20 units with a total profit of 540. And then just to make it more concrete, so this is the example that we can apply the transformation above. Again, we have 3 products, and we have limiting resources on hours of machining, grinding, and assembly. And we are given unit profit of product 1, 2, and 3. And also we have a setup cost of line product 1 of 1,000, and product 2 and 3 is 800 and 900. Okay, let me highlight. So 48, 55, 50, 1,000, 800, and 900. Okay, so we can just apply what we learned up there. So xi is a quantity of product I to produce, and wi is 1 if produce product I and 0 otherwise. And then we just maximize net profit. So profit minus the setup cost, and then the constraints are on the time used cannot exceed time available. And yeah, so we just have the parameters from up here. and then if we produce x1, we have to set up. So these are relationship between x's and w. And then m can be any large positive number, upper bound of xi. I think I use 100 or 100 or 1000 or something. So yeah, you can just try with the numbers. And then I'm not going to solve it for you, but if you do it for yourself on the Excel sheet, you can actually duplicate this sheet, and then like this is the fixed charge. You can duplicate this sheet and then just fill in parameters, because we already did the Excel formulas and solver dialog, so that makes it faster. And so okay, so just before we move on to the next topic, potential pitfalls is that do not use if Excel function if to model the relationship between x's and binary decision variables, because this will not work with the solver. The if function is nonlinear. And treat the binary decision variable just like any other variable. Make them changing cells. If you don't make them changing cell, you cannot say that they are binary. Okay, and just modification of this problem. Suppose we have another constraint that the company does not produce any unit of product 3 unless it produce at least 40 units. So how do we specify the constraint without using if? So this is what we have earlier, x3 less than or equal to mw3, and we add the minimum lot size as x3 greater than or equal to 40 times w3. Okay. And then we can also use binary decision variables to model piecewise linear function. Suppose x is integer value and we have the following function, like for x between 0 and 3, y equal to 2x, and for between 4 and 7, it is this function, and for x between 8 and 9, it is this function. So if we plot it out, it's actually this continuous function, like here. So we are going to use three binary variables, W1 for the first piece, and W2 for the second piece, and W3 for the last piece. And then we're going to let X1, X2, and X3 be integer. Uh, Here, because we assume up here that X's are integer value. So we define Wi in terms of xi. So W1 is 1 if x fall into the first range, and x1 equals to x if x is in the first range. And W2 for the second chunk. So W2 equal to 1 if x falls into this range between 4 and 7, and x W3 is for the large chunk. Okay, 7, 8, and 9. And so we are going to modify this piecewise linear function as follow. So only one Wi will be 1. So we can say that the sum of all W equal to 1. And we have to have the condition between xi and Wi. So for the first chunk, so x1 is between 0 and 3 W1, because if W1 is 0, then x1 is 0. And then x2 is between lower bound times W2 and upper bound times W2. And for X3 is between the last piece. And then only one axis will be non-zero. So X is a sum of all these x's. And we transform this equation 5 piecewise linear function as this one. So y equal to the sum of the w1 plus 2x1, 9 w2 minus x2 minus 5 w3 plus x3. And wi's are binary and x's are non-negative integers, and we also need all these conditions up here as well. Okay. And the next one is we are going to look at the problem of quantity discount. This is actually the problem that we I think in this class we didn't do it, but then it appears earlier. But now we're going to add more details to it. So the company produced two products, two types of bathtubs, Aqua Spa and Hydrolux. And then these two products use common parts like pumps, and then they also consume labor hours and the resource of tubing. And one unit use one pumps and one unit of Hydrolux use one pump. And then we have 200 pumps available and 1566 labor hours and 2,880 feet of tubing. And then so we for anything below 75 units, we get a profit of 5,350. And if we produce more than 75, we get unit profit of 375. And also like here, so as we produce more, the unit profit is different and higher. So here, that's what I mean by this. Okay, this is what is explained down here. And then, so we want to formulate this problem as a math model, linear math model. So again, we assume we have two, actually four decision variables. X1 for Aqua Spa below 75, and then X1 plus is what we produce above 75, and X2 is the amount that we produce less than 50 units, and X2 plus is anything beyond 50. So we max total profit, right? 350 x1 plus 375 x1 plus 300 x2 plus 325 x2 plus. And we have the resource constraint on the pump. So one Aqua Spa and one Hydrolux use one pump. And then also on the labor, and then on the tubing. Okay, so if we produce more, we also need to use resources. And then what is interesting is how we model the cut point 75 and 50. So we declare two decision variables, binary decision variables. W1 is 1 if we produce more than 75 units of Aqua Spa, and W2 is 1 if we produce more than 50 units of Hydrolux, and these are 0 otherwise. So we have to say that X1 greater than or equal to 75 W1 and X2 greater than or equal to 50 W2. I mean, it looks like it doesn't make sense, but and then also X1 plus less than or equal to MW1. I think let's look at this one. It's easier to understand. So if we produce more than 75, W1 is 1, then X1 plus can be positive and also X2 plus. And then so, I mean, if W1 is 1, X1 is at most 75 because X1 plus has a higher profit. So this formulation is actually working. So, and then also we want to find a nice value for the M, and because we have the total of 200 pumps, so these constraints makes sense that we can set M to be 200. Okay, so we can solve for this problem on Excel. Let me see. Okay, so here, so this is a unit profit, and then I have to say the pumps required is 1111, and then nine 350 ah aqua spa hydrolux aqua spa. Oh, okay. So 350, 300, 370. Okay. So 9 um 9 6 9 6 and then 12 16 and then 12 16 also, and then available is 200 on 1566 and 2880. Okay. And then we put okay, our m, oh actually I just say m is 200. So m times w oh okay this times w1, and then we can just copy. I think it automatically times w2. Okay, and then x this one minus, okay, and then okay, and then we have to figure out the um, total profit is some product of amount and then the unit profit, and then I think I can just copy. Okay, so just copy. Okay, it works. So I can just copy them down, and then I'll just call up the solver. So I want to maximize total profit. Changing variables are cells are this axis, and also the W1, W2, and the constraint is that this is less than or equal to the right hand side, and then all this thing greater than or equal to 0, add, and then this is less than or equal to 0. And then I have to also say that this is binary, and then this is integer. I think that's it. Okay. Oh, now this makes sense. Okay. So we can see that we produce 75 of aqua spa at the 350, and then the thing beyond that, there's a 47 unit of aqua spa beyond that, and then we at the lower bound of hydrolux is 50, so produce up to the lower bound, and then we produce extra more. So you can see that using binary decision variables allow us to do quantity discount like this.